So, Andre, it's lovely to introduce you all to Andre. He's a member of the strategy unit. He's one of our healthcare analysts, and I ask you to introduce your title, Andre. I read it and went, I'm not sure I can say half of those words. So, in proper respect for you, Andre, I am going to say um, your chat is 25 minutes long, and will there be time for me to join you in the last 5 minutes for questions, or do you think we'll use up all the time?
Yes, hopefully there should be a bit of time for questions at the end,
Lovely.
maybe.
So I'm going to come in
Yeah,
about.
hopefully 5 minutes, although we'll see. I might eat into that a little bit.
Yeah, don't worry. I'll sit quietly, waiting for you to finish, and I'll come in about 12:15. So I'm going to hand over to Andre now to introduce his presentation, and then his slides will come up on the screen in the usual way. So
What about now?
Perfect.
Is this
Yeah, you're all good
perfect?
now.
Okay,
And
awesome.
Julie,
Okay,
hear
nice.
me.
Okay, great. So my name's Andrea Bilborough. Yeah, as Karen said, I'm a healthcare analyst in the strategy unit. And this talk is nominally an impact evaluation of the mental health rough sleepers program. Although kind of what it really is about, it's a kind of methods talk really about extending synthetic difference and differences, which is a common impact evaluation technique, to non-normal outcomes. So it's kind of quite a complicated setup that we ended up using in this impact evaluation. But I think the scenario and the problems we had to face in it are like really super common in impact evaluation. So hopefully there's a lot for other people to take away here. So just quickly, I'll do some kind of like super background context. So the program that we're evaluating is the Mental Health Rough Sleepers program. So essentially between 2019 and 2023, the Mental Health Rough Sleepers program set up 37 services targeting mental health and rough sleepers. So all of these were based in areas which were determined to have like high need for that area. I think the investment through NHS England was approximately £30 million, although a lot of these services also kind of enhanced that budget from other sources. It is obviously primarily aimed around mental health, although I think talking to the services, a lot of them had a really kind of holistic understanding of that and really wanted to link into lots of other kinds of services, and also some were more or less focused around physical health as well for rough sleepers. So from the perspective of the impact evaluation, the kind of key outcomes that we're interested in are increasing accessibility of elective services for homeless people and reducing demand for acute services for homeless people. So in terms of the evaluation more generally, so firstly, the impact evaluation I'm going to talk about today and the method is only one part of what was a much larger evaluation. There was like a really large qualitative component, all about service models and enablers and barriers. There was a cost survey and a cost consequence analysis, but I'm not really going to talk about these things in too much detail today. So the kind of basic setup in terms of the intervention, which I think is pretty common, right, is you have lots of control units. There was lots of areas that didn't receive a mental health rough sleeping service. And then you have lots of eventually treated areas who all received the treatment at different times, because some of them received it in 2019, some in 2020, or all the way up to 2023. So in terms of the challenges for an impact evaluation, the kind of core one, right, is that areas that don't have mental health rough sleeping services are not necessarily fair comparisons to areas that do have mental health rough sleep services, because they could be super different, not just in like scale in terms of the absolute level, but also just like in the overall trend over time. There's also substantial variation in when the mental health rough sleeping services were introduced, which in a way seems like it shouldn't be too much of an issue, but anyone that's been involved with the difference and differences literature knows that in kind of surprising ways this can actually cause a lot of biases in ways that you might not expect. We also expect there to be pretty heterogeneous impact, which is just to say that the impact of services will vary pretty substantially between different services, and also even within a service at different points in time. So this is the kind of classic setup that I think is super common across, that I see all the time in impact evaluations. This particular project had a couple of other kind of key challenges, right? So one was identifying the boundaries of which NHS services were affected by which mental health rough sleeping services, and also identifying homeless people within available national data sets is also kind of tricky and messy. But yeah, I'm not going to talk in too much detail about these last two. I'm going to try and keep it general to the more general context of those first three issues. So let's pull back a little bit. Let's just talk in super kind of general terms about methods. I'm going to start off talking about difference and differences, which is the kind of basic bread and butter that loads of impact evaluation is based around, and then synthetic difference and differences. At first, I'm just going to use some simulated data to kind of get a rough idea of the structure. At first, I'm just going to talk about assuming one treated unit, although obviously in the real case, we had lots of treated units, which does complicate things a little bit. Okay, so this is a kind of example scenario, right? So I've simulated some data. This is following quite a kind of basic setup. So we only have one treated unit, which is on the bottom panel, and multiple untreated units, which is on the top panel. So the y-axis is an outcome. It could be whatever you want. So let's think about A&E attendances by homeless people, for example. And then the x-axis is time. So as you can see, all of these units kind of follow the same trend broadly. Some obviously are higher on average and some are lower on average, but they do broadly seem to follow the same kind of pattern over time, up to time point 80, which is where our fictional intervention happens, where the two appear to diverge. So this is the classic kind of difference in difference scenario. There's lots of ways of analyzing this. Essentially, you need to adjust for the units and also adjust for time. There's various different ways of doing it. The most obvious, right, would just be to run a two-way fixed effects. But there's lots of options here, right? As this is simulated data, I can just see what the outcome would have been without the intervention. So in this data set, this is this green line that I've simulated that is in the bottom panel. And the difference between the green line and the black line is the impact of the intervention. Now, obviously, in the real world, we don't ever know what a unit would have had without the intervention like perfectly. So we need to get rid of that. We're going to need to estimate that. So thinking about that kind of basic setup, that bread and butter setup, well, the first thing is, right, so we only have one treated unit. And actually, when this method becomes generalized to multiple treated units, you can actually induce bias in some kind of quite surprising ways. You can get full sign reversals as well, where a positive impact looks like a negative impact just because you have multiple treated units, which was super surprising when that was discovered. Although there are obviously more complicated variations on this method which resolve this, right? I think there's the DID package in R by, I think it's Callaway and Santana, which is really, really nice and is one way of solving this problem. But the kind of broader issue that we're going to talk about here is the assumption of parallel trends, right? So the standard difference and differences assumes that all the units follow basically the same trend over time, apart from the impact of the intervention. In general, this is often pretty implausible, right? Or at least we can't know it in advance. So for example, in our context, we'll be interested in like A&E attendances by homeless people. And so how confident would we be that the same trend over time happens in Westminster and central London as what happens in, like, let's say, a rural area outside of London? So to be clear, the issue is not just that the level or absolute value on average might be different between those two places, but also that the like factors over time are quite different. And so they're actually going to follow different trends over time, right? So you might even get people migrating from the rural area to Westminster because there's more support there. And so they're going to have negative correlation at some points and maybe positive correlation at other points, right? So this is the kind of big challenge. So let's simulate some data that's the kind of more realistic setup, right? So here we have still one treated unit on the bottom panel. And on the top, we have some control units, which look pretty comparable to the treated unit, but we also have a load of other untreated control units, which seem to be following a completely different trend, right? So this is simulated data, right? So I can just tell you for a fact, basically how I did it is all these blue ones are simulated from one kind of pattern, and then all these red lines are simulated from a different pattern, right? So essentially, when we're running our analysis, what we want to be able to do is compare our treated unit, the blue line, to the blue control lines. We want to compare it to the fair comparisons and not compare it to the red ones, which are like just doing something completely different. Anyway, obviously in the real world, we don't know what is a fair comparison and what is an unfair comparison, like advance of time. So, I mean, this is like essentially the challenge. So basically what we need, right, is a kind of principled way to create a fair comparison using only the good blue control units and ignoring the bad red control units. So it's worth noting that in my simulated data, the controls are either good or bad. In the real world, it's going to be much more blurred, right? You're going to have a load of kind of okay controls and stuff in between. And this is where you get synthetic methods, right? So you get synthetic control and synthetic difference and differences. Generalized synthetic control kind of fits in this space as well, although it's doing something quite sophisticated and different underneath the hood. But essentially the idea there is you create a synthetic counterfactual, a synthetic comparison to the treated unit, and you do that by reweighting the control units plus an intercept, depending on how you do it, so that the synthetic counterfactual matches the treated unit in the pre-period. So this is all a bit abstract. Let's take an example. Let's say that you have an intervention that only happened in Birmingham and nowhere else. Basically, you try and create a synthetic Birmingham. And so how do you create this synthetic Birmingham? Maybe you try, well, let's just go 100% London and see how well that outcome matches Birmingham in the pre-period. And you say, oh, that doesn't match that well. Okay, let's try 90% London, 10% Cornwall. See how well that matches. Then 90% London, 10% Leeds, and see how well that matches. And then you take whichever combination predicts the outcome for Birmingham the best in the pre-period. So in reality, this is going to be done by like a complicated optimization algorithm. You're not going to be like manually checking all of them, right? But this is the kind of core idea for creating a synthetic treated unit. So now that you have a synthetic treated unit, you can compare the actual outcome from the treated unit to the outcome from your synthetic unit in the post period as a way of estimating impact. So essentially, Birmingham gets compared to synthetic Birmingham, which is in reality just 80% Leeds and 20% London, or whatever the exact numbers are. Right? In synthetic difference and differences, the process is then repeated with time weights. So essentially, like 2025 gets compared to synthetic 2025, which is like, you know, some weighted version of other years. I'm not going to talk about that bit of the process too much. This does increase robustness, although it comes with certain costs as well. So why not just use classic synthetic difference and differences, right, for our analysis, right? So it's a real class. I mean, it's only been around for 6 years, but I think it's a real breakthrough in the field. It's a super robust method. It's more efficient than some of the rivals. And this is basically a super common setup, right? So you're unsure what's a fair comparison. It works really well if you have heterogeneous treatment effects, which I talked about earlier. And there's a great R package that you can use called SynthDid, which is by Athi, Arkangelski, Imbens, and Hirschberg, I believe. But yeah, super easy to use, super clean. So why couldn't we just use that in our analysis? So classic synthetic difference and differences basically assumes that all the units are on the same scale. So if Birmingham increases by 10 one month and then decreases by 5 the next month, it's being compared to units which also vary on approximately that same scale. They also change by approximately 5 or 10 a month, or at the very least, they can be averaged in such a way to do so. However, in our case, we have outcomes on super different scales. In particular, the control units are on average way smaller than all the treated units. And this is because the program really efficiently targeted areas where there's loads of homeless people. So basically all the areas that have really high levels of homeless people have a mental health rough sleeping service, and all the areas that don't just tend to have much fewer homeless people. So we're comparing areas with few homeless people and subsequently little absolute variation to areas with high numbers of homeless people and so much higher variation. This will cause the weighting scheme to kind of fall apart. There's also zeros in the control units, which also kind of complicates things in certain ways. So you get months where like a particular A&E just didn't see any homeless people. But like across all the A&Es that didn't see any homeless people, you might have some useful information in there. So that's kind of the challenge. So how can we extend our method in order to kind of adjust for this issue, right? So let's return to classic synthetic difference and differences and think about how that works. So classic synthetic difference and differences creates the synthetic control. So how does it do that matching process of matching the treated unit to the reweightings of the control units? It does that by minimizing the sum of the squared residuals between the controls and the treated unit, right? So that process of choosing weights which minimize the squared residuals, that is basically just finding the maximum likelihood weights, assuming normality, essentially. And really all our issues here, and there's other issues I haven't really talked about here, all of these fall out of the fact that the method is assuming normally distributed outcomes, and our outcomes are small counts, such as A&E attendances, or in some cases they're rates as well. So we're also interested in like the did not attend rate for mental health appointments, things like that. And so these don't actually really follow, the errors are not going to follow normal distributions, whereas our method is kind of going to assume that they do. Now, the nice thing about thinking about this as a maximum likelihood function is that we can essentially reapply the procedure to any family and just change that likelihood function. You change the optimization algorithm so it's maximizing the likelihood for whatever family you want, rather than just minimizing the sum of squared residuals specifically, which only works for the Gaussian outcome. You can maximize the likelihood for, in principle, any statistical family you want. So for us, we're interested in counts such as A&E attendances, so the natural family is the Poisson, and for rates such as did not attend rates for mental health appointments, the natural family is the binomial. So essentially, that's like what we did, right? For the mental health rough sleeping evaluation, we basically remade the entire synthetic difference and differences procedure, but we did it in such a way that we can now change that likelihood function to work with whatever we want. I cannot emphasize enough, this took absolutely forever. It was like so long, and we ran into so many problems that I'm not going to talk about here. But this does effectively solve the problem for us, and also it means it can be like quite neatly extended for any other distribution that would be relevant as that comes up. One thing I haven't talked about in too much detail here is how we estimate uncertainty. So like p-values and confidence intervals. Again, I'm going to try not to get too deep into the weeds here, into the weeds here. But essentially, so the way to estimate p-values and confidence intervals is that we do like a placebo test. So essentially, we pretend that the relevant control units received the treatment, even though they didn't. And then we assess what impact the method estimates for those control units, right? So let's go back to our example where the intervention happened only in Birmingham and nowhere else. We would then run the procedure again in Leeds and say, this method, what impact did it find in Leeds? And we know that the true effect is 0 in Leeds because Leeds didn't receive the intervention. And then if the method says, well, Leeds had a really large effect, then we can say that, well, it's probably not that accurate in Birmingham either. Whereas if it says that the impact was really small, really close to 0 in the case of Leeds, then we can have more confidence in the case of Birmingham as well. So essentially what we're building here is an empirical null distribution, and then we can use this formally to kind of construct confidence intervals and p-values. So there's kind of an extra complication, which I'm not going to talk about too much here, right? Which is that in practice, we often have multiple treated units. So we need to run this procedure for this placebo test for in a comparable way for all of the treated units, and then kind of aggregate all of that and all of those effects up to get the aggregate impact, but also all of that uncertainty up in such a way to get kind of aggregated uncertainty. So that's the kind of procedure. In terms of so we can't actually make the code for the actual analysis available, although the code not with all the data is available on GitHub. The code for counts is super clean and easy to use. The bit on rates is a little bit, I still need to tidy that up a little bit. But essentially we kind of streamlined this down to run it such that running the analysis is now like pretty straightforward, even though each of the functions, there was a lot of work put into building them. So essentially this is what the final analysis will look like, right? So it's like you're just running 5 functions in row. You just need to tell it what the data set is and the treated units, and then everything else kind of follows just from that. You can do 2-sided, 1-sided inferential statistics. So that's the kind of method, which is in some ways the big output from this. But I want to briefly come back to the mental health rough sleeping program, which is the reason we all did this, right? And talk about the actual findings in that specific program. So we had a load of outcomes to do with accessibility, and there were I think that all of them to do with accessibility were in the right direction, but there was no statistically significant impact on any of those measures. There was also no detectable impact on the number of emergency admissions. Although it's worth pointing out here that the confidence intervals were actually like pretty wide in a lot of them. Some of that's due to the method, although some of that's also to do with those other issues that I mentioned earlier, to do with like cleanly identifying homeless people, and allocating areas to services, and also a lot of this is just like quite a difficult problem, like statistically, right? When you have lots of very small control units that you're trying to use to predict much larger treated units. However, the significant findings were that the mental health rough sleeping service caused, on average, a reduction of 13.61 attendances to A&E per month per service by people who have been homeless within the period studied. So the p-value is less than 0.01. This is actually like a massive effect. This is really large. And it also caused a reduction in emergency admission length of stay of 0.28 days per admission. Again, a really small p-value. Although this second one was done using kind of the more conventional synthetic difference in differences method. This is a graph of what our findings are, although I'm worried that I'm running out of time. So
you are a little bit, Andre, but as Sam Finnegan has said, and lots of people have agreed with her, this is a very clear and well-delivered talk for something so technical, not easy to do. And I've been texting somebody behind here going, I totally agree. I can't believe how brilliant Andre's presentation is. So compelling, interesting. But I did have to ask the audience for questions. So
yes.
I just want you to know that I have gone to the audience for the questions, because
nice.
way beyond my abilities. So you've got 3 questions.
Nice.
And I think we need to finish at 20 past. I'm just going to ask the one that's got voted the most from Chris May. And I'll let you, because I don't know how to now can I share that? Oh, yeah, you can see the question yourself now up on the screen.
Okay, so when applying these methods to Poisson and binomial models, have you made any adjustment for over-dispersion? Some of this could be the within-between effects you mentioned, but there's often residual variance. Yeah, this is a great question. So, broadly, no. I think our first step was to get the rough structure right. And so moving to a Poisson improvement over just using a normal distribution, I think... I think so. In the case of the Poisson, it would be really nice to do a negative binomial, which has a really nice, well-defined likelihood. Quasi-Poisson, I think, does not. So that would be a goal further down the line. It's a lot more difficult to estimate because you're trying to optimize multiple things at the same time, because you need to kind of adjust that over dispersion parameter. I think it probably is feasible and is something we'd like to look at in the future. But for this project, we're super happy to make the progress to a Poisson model from Gaussian, essentially.
One of the other questions was, could you share the link to GitHub in the attendee chat in a minute? But then this is that.
Difference in another supporting services will have impact. How did you allow for the difference in other supporting services that will impact on the numbers? So in essence, we didn't do anything directly to adjust for the differences that. So I think the question is right. Some areas will have lots of other mental health provision in that area, and some areas won't. So how do we kind of adjust for that issue? So broadly, we don't do anything directly, but the idea is that if the trend in like Birmingham has X type of support, and if that trend matches our synthetic control across all of the pre-period to whatever the synthetic control is, then it should be kind of adjusting for that issue implicitly, even though it's kind of agnostic as to what kind of other services are in that area. It should just do that by being able to match in the pre-period. You obviously can get issues if other supporting services change like around the same time or during the period that you're studying. But yeah, that's just a kind of risk, I guess. Thanks a lot.
Thank you very much, Andre. We've been able to do your full presentation, be really interested, and some great questions from the audience. So spot on, done. Thank you very much. And